In this module we will discuss electric flux and Gauss law. Electric flux happens when a flow of electric field lines passes across an imaginary surface area. Electric flux can be written as a function as shown in equation A. We see that the electric field is perpendicular to the imaginary surface. The unit of an electric flux is given as a Newton meter squared over Coulomb. Here the same imaginary A area is tilted by some angle and we determine the electric flux equation to accommodate this change. We see that the amount of electric field lines that are caught in the tilted area is reduced. The function that accommodates these changes is given by equation 2 and we see that it is the cosine function of the tilt angle phi. When the angle between the electric field and the area is 0, then the electric flux is maximum. So if the tilt angle phi is 0, then it gives a maximum electric flux. For this case, when the tilt angle is 90 degrees, it gives an electric flux of 0 as shown in equation 3. We can visualize it and see that there are no electric field lines contained inside the imaginary area. Sample problem. A disk of radius 0.1 meter is oriented with its normal n-hat unit vector at 30 degrees to a uniform electric field E of magnitude 2 times 10 to the power of 3 newtons per coulomb. Letter A, what is the electric flux through the disk? Letter B, what is the flux through the disk if it is turned so that the unit vector is perpendicular to the electric field? Letter C, what is the flux through the disk if the unit vector is parallel to the electric field? For letter A, let us determine the A electric flux when the disk is tilted to 30 degrees with respect to the electric field direction. We recall the expression for the electric flux as shown in equation 2. We see we need to write an expression for the area of a circle which we see in equation A. We then substitute this equation for the flux and we get a value of about 54 Newton meters squared per coulomb. For letter B, let us determine the flux through the disk if it is turned so that the unit vector n-hat is perpendicular to the electric field. So we see that the disk is lying parallel to the field when its area vector is pointed perpendicular to the electric field. So as expected we get 0 flux. For letter C, let us determine the flux through the disk if the unit vector Ni is parallel to the electric field. Now we see from the figure the disk is lying perpendicular to the field when the area vector n-hat is lying parallel to the field. This would result in a cosine 0 equal to 1, which gives a maximum flux value, and it is about 63 Newton meters squared per coulomb. Sample problem. An imaginary cubical surface of side L is in a region of uniform electric field. Find the electric flux through each face of the cube and the total flux through the cube. Letter A, it is oriented with 2 of its faces perpendicular to the electric field. Letter B, the cube is turned by an angle about a vertical axis. Refer to the figures here. For letter A, to find the electric flux where the box is oriented with 2 of its faces perpendicular to the electric field, we refer to the figure here. Let us determine the flux generated by each faces of the cube with respect to the orientation of the electric field. For area A1 we refer to the unit vector n-hat1 for its direction, and we see that area is oriented with respect to the electric field as phi equals 90 degrees, so we have the flux equal to 0. So we see that the electric flux when the angle between them is 90 degrees results in a 0, so that means the areas that have this property will also have a 0 flux, and they are area 2, area 5, and area 6. So we are left with areas 3 and 4 whose directions are not perpendicular with respect to the electric field. For A3 the angle between as indicated by the unit vector n hat 3 is phi is equal to 0 degrees, so that means that the electric flux is given as shown in equation A. For A4 the angle between as indicated by the unit vector n hat 4 is phi is 180 degrees, so that means that the electric flux is given as shown in equation B. Note that since this is a cube, then all the faces have the same area, which is equal to L squared. So now the total flux, which is just the sum of the individual flux from each face, is now calculated. We see that the resulting flux is equal to 0. The closed surface demonstrates that in absence of a charge inside it, it will have a total electric flux equal to 0. For letter B, to find the electric flux where the box is turned by an angle beta about a vertical axis. Refer to the figure for more details of beta position. So we see that there are two faces that have an angle of phi 90 degrees with respect to the electric field, and they are area 1 and 2. These areas will produce 0 electric flux. The other faces are oriented by some angle beta and theta, which we will examine further. Let us look at the box in the perspective viewed at the top as shown on the figure. We see that the top view the positions and orientations of the 4 remaining areas. So here we are able to identify the angles with respect to each face and the relation of the angles beta and theta, which are shown by equation A. Now we proceed to calculate these 4 areas, and starting from area 5. The angle between the electric field and the area 5 is A phi equals 180 degrees minus A beta. Using the mathematical identity for cosine function, which is given by equation B. So for area 5 the electric flux is given as in equation C. For area 6, the angle between them is just beta, so that means the electric flux is given simply as in equation D. For area 3 we have the angle between them as phi equals 90 degrees minus beta. We also consider the mathematical identity here. So we have the electric flux given as equation A. For area 4, the angle between them is phi equals to 90 degrees plus beta. Applying also the mathematical identity for cosine here. So the electric flux generated by area 4 is given in equation F. So the total flux for the tilted cube in the presence of an electric field is the sum of the individual flux from each face, and we see that it sums up to 0. The closed surface demonstrates that in absence of a charge inside it, it will have a total electric flux equal to 0. Sample problem. A point charge q equals 3 microcoulomb is surrounded by an imaginary sphere of radius 0.2 m centered on the charge. Find the resulting electric flux through the sphere. Here we have a sphere-shaped imaginary surface with an area given in equation A. Recall the expression for the electric flux as shown in equation 2. Note that the electric field is radiating out from the positive charge. The sphere, where an infinitely small area has a direction which is also radiating outward. Which means that the angle between the electric field and area vector is 0. Substituting this back to equation 2, and we have that the electric flux generated by a charge through a spherical surface is about 3.38 times 10 to the power of 5 Newton meters squared over Coulomb. Here we see that the amount of electric flux is dependent on the charge, not on the size of the container as indicated by the equation where the radius is cancelled out. What matters is what is contained inside the three-dimensional container like this sphere. In this part we will talk about Gauss' law. Gauss' law states that the total amount of electric flux passing through any closed surface is directly proportional to the enclosed electric charge. Gauss laws are ideal for charged objects that have high symmetries such as uniformly charged straight wire, uniformly charged infinite plate sheet, and uniformly charged thin spherical shell. Gauss law is expressed mathematically as the charge enclosed over the electric constant as shown in equation 4. Considering a point charge, the electric field lines radiate from its center. A point P at a distance r will experience an electric force due to the electric field. The expression that takes into consideration these field lines due to a point charge is given by equation 5. This equation takes into account the shape of the field lines, which is taken to be a spherical shape. So we have a spherical Gaussian surface. Enclosing the charge with a sphere, we can get the Gauss flux. As mentioned earlier, the Gaussian surface is shaped to be a sphere due to the symmetry promoted by the point charge, which creates electric field lines like a sphere. If we take a representative area A in green, we see that the area and the electric field lines are parallel or pointed in the same direction, which is radially outward. The Gauss flux expression is then given by the equations here, and for having the same direction of the area and electric field lines, the angle is 0, so the cosine function is equal to 1. So we have the Gauss flux is given by equation 6, which is the charge q over the electric constant. In this case, we double the size of the Gaussian surface in the sense that we double the radius, which becomes 2r. Doubling the radius of the Gaussian sphere, the area increases 4 times. The electric flux through the sphere is now equal to equation 7. So regardless of the size of the Gaussian sphere, the Gaussian flux remains the same, which is the charge contained within the sphere. Here we have a three-dimensional image of the Gaussian surface for both scenarios, where the second image on the right is where the radius is doubled. In this case, we use an arbitrary shaped Gaussian surface where its area is given as a function of cosine phi. For an arbitrary shaped Gaussian surface, we use integral function in order to accommodate the irregularity of the shape. Equations 8 and 9 can be used to solve for the Gaussian flux. Ideally, we would choose a familiar shape of Gaussian surface, since it would be integrated easily, such as spheres, cylinders, and sheets. Here we have a three-dimensional view of an arbitrary shaped Gaussian surface. The Gaussian flux is adapted for various objects, including Gaussian surfaces that are irregular, and we write a general expression for it, and it is given by the equation 10. We see that it is able to calculate several physical quantities. Using this general expression, you can solve for the value of the electric field if there is enough symmetry that you can solve the integral part and the charge distribution. The reverse is also true. If you are given the electric field, you can solve for the charge distribution of the charged object. A key aspect in solving problems like this is to use symmetrical Gaussian surfaces, i.e., if the charged object is a sphere, then the ideal Gaussian surface would also be sphere-shaped. For a uniformly charged solid conducting sphere, if charges are contained by a media, it resides close to the surface for both solid or thin hollow objects, as shown in the figure. If we measure the charge enclosed by Gaussian surface A, which is inside the sphere, we get the Gaussian flux is 0, since there is no charge enclosed. This is because the charges lie near the surface. So the Gaussian flux is 0. The electric field can also be calculated using the Gaussian function. We see that the electric field is also 0, since there is no field generated inside the Gaussian surface. The use of a spherical Gaussian surface is an advantage in integrating the function easily. If we use a Gaussian surface that encapsulates the entire solid conducting sphere as shown in the figure, the Gaussian flux is non-zero. The charge enclosed is equal to the number of protons contained, which is 12 protons. The electric field is also obtained using the same equation. We see that the electric field is non-zero as shown by the calculation here. Sample problem. Determine the charges enclosed for the different Gaussian surfaces. For case A, the enclosed charge is positive Q. For case B, the enclosed charge is negative Q. For case C, both charges are enclosed. Since they are of opposite types of charges but equal in magnitude, we have the sum equal to 0. For case D, the Gaussian surface encloses no charge, so it is also 0. Sample problem. A point charge Q equals 3 microcoulomb is surrounded by an imaginary sphere of radius 0.2 m centered on the charge. Find the resulting electric flux through the sphere using Gauss' law. To find the electric flux using Gauss' law, we use as shown in equation 10. So simplify and solve for the flux, since it is reduced to the absolute value of the charged enclosed over a constant. We see that it results in a value that is about 3.38 times 10 to the power of 5 Newton meter squared over Coulomb. Here we see that the amount of electric flux is dependent on the charge, not on the size of the container as indicated by the equation where the radius is cancelled out. What matters is what is contained inside the three-dimensional container like this sphere. Let us try to find the electric field produced by this charge using the spherical Gaussian surface using equation 10. We integrate this over the spherical area, which is 4 pi r squared. So we have equation 10 manipulated and we arrive at an expression solving the magnitude of the electric field as shown here. Sample problem. We place a total positive charge Q on a solid conducting sphere with radius r. Find the electric field at any point inside r1 less than the radius of the sphere and outside the sphere r2 equals 2r and r3 equals 2r. Let us consider the electric field when r1 is less than the radius r of the sphere. We use the Gauss law expression. Since the material is a conductor and the charges lie only near the surface, which means that the charged enclosed is 0, then the electric field due to the Gaussian surface is 0. Let us consider the electric field when it is at radius r of the sphere. We use the Gauss law expression. And we see the electric field. Let us consider the electric field when r2 is greater than the radius r of the sphere. We use the Gauss law expression. Here r2 is equal to 2r. So we have the electric field by this Gaussian surface as shown here. Let us consider the electric field when r3 is greater than the radius r of the sphere. We use the Gauss law expression. Here r3 is equal to 3r. So we have the electric field by this Gaussian surface as shown here. Here we see that as the radius of the Gaussian surface increases, the magnitude of the electric field is reduced as shown by the graph here. We call this an inverse relationship. For the radius less than r is 0 for conducting spheres, and the electric field begins at the surface of the sphere where it is at maximum and reduces as the radius increases. For a solid conducting material that has an irregular shape, the excess charges will still reside on the surface of the material in order to create as much space due to repulsive interaction with each other. Here we have a hollow conducting sphere. The excess charges will reside on the outer surface of the conducting sphere to create as much distance from each other. It would prefer to choose the outer surface since by nature the excess charge would repel each other, pushing each other at a maximum distance. But if a positive charge Q is placed in the cavity of the conductor, then what happens is that the charges in the conductor redistribute in such a way that negative charges appear in the inner surface equal to the amount of positive charge in the cavity. The opposite charge on the inner surface has an equal magnitude as the outer surface. Here we have a solid charged surface and the charges are distributed all over the body evenly. Drawing a Gaussian surface with a radius r inside the sphere will result in a non-zero Gaussian flux. This is probably because non-conducting surfaces resists the flow of charges, thus inhibiting the movement towards any favored direction of the charges. This perhaps keeps the charges stationary or less likely to migrate, thus keeping the uniformity in its charge distribution. Here we have a solid charged surface and the charges are distributed all over the body evenly. Drawing a Gaussian surface with a radius r inside the sphere will result in a non-zero Gaussian flux. This is probably because non-conducting surfaces resists the flow of charges, thus inhibiting the movement towards any favored direction of the charges. This perhaps keeps the charges stationary or less likely to migrate, thus keeping the uniformity in its charge distribution. Sample problem. A solid conducting sphere of radius A has a net positive charge 2 quetzales. A conducting spherical shell of inner radius B and outer radius C is concentric with a solid sphere and has a net charge negative Q. Using Gauss' law, find the electric field in the following regions: letter A, R less than A, for letter B, where R is greater than A but less than B, for letter C where R is greater than B but less than C, and letter AD where R is greater than C. A. Let us first examine the structure and direction of the electric field based on this problem. We see here that the electric field comes out from the positive 2q and ends at the surface of the outer sphere with negative q. Note that the field is still able to generate a field outside of the electric field since the core has twice the number of positive charges than the shell. For letter A, let us examine for radius A r1 less than A. We recall Gauss' law as shown in equation 10. Since the material is a conductor and the charges lie only near the surface, which means that the charged enclosed is 0, then the electric field due to the Gaussian surface is 0. For letter B, let us examine for radius r2 greater than A but less than B. The charged enclosed is the inner conducting sphere with charge 2 quetzales. So the electric field is given in equation A. For letter C, let us examine for radius r3 greater than B but less than C. The charged enclosed is the inner conducting sphere with charge 2q and the inner surface of the outer shell with a charge of negative q. The charges that are opposite sign reside on the inner surface but only q. The electric field is given by equation B. For letter D, let us examine for radius r4 greater than C. The charged enclosed is the inner conducting sphere and the outshell, which is just 2q plus the negative q, so the net charge enclosed is q, so the electric field is given in equation C. Here we can compare the behavior of the electric field as the Gaussian surface is getting larger and larger. We see that it becomes reduced as it moves away. Sample problem. A positive charge is distributed uniformly throughout the volume of an insulating sphere with radius r. Find the magnitude of the electric field at point P at a distance r from the center of the sphere. Using Gauss' law equation, we calculate the electric field generated, shown in equation 10. Solving for the electric field, we have equation A. Since the material is a non-conductor, the charges are spread uniformly throughout the sphere, and we will take only a portion of the charges contained inside the Gaussian surface here. The goal here is to get a ratio of the volume contained by the Gaussian surface with respect to the total volume. To obtain the ratio of the volume contained and total volume, we use the volume charge density. Since we have assumed that the charges are uniformly distributed, we can write equation B. Rewriting the expression for the charge enclosed, we have equation C. Substituting the expression for the charge enclosed back to our expression for the electric field, we have the electric field generated by the charges contained inside the Gaussian surface. So here we have the graph for the electric field, and we see that it starts from the origin, then gradually increases to a point r where it is maximum, then it proceeds to decrease. For a solid conducting thin wire, the charge density is given by the linear charge density as shown in equation 11. We see that the Gaussian surface for a wire has cylindrical shape as shown in the figure. Its electric field direction is of the same direction as the area for the body of the cylinder. Sample problem. Electric charge Q is distributed uniformly along an infinitely long thin wire. The charge per unit length is positive lambda. Find the electric field using Gauss' law. Using Gauss' law equation, we calculate the electric field generated, shown in equation 10. Solve for the electric field and take into consideration that the area here refers to the cylindrical Gaussian surface. We have equation B. We now consider the charge enclosed, which we will use the linear charge density to create a function for it. Considering the linear charge density in relation to the charge enclosed, we have equation C. Since the linear charge is a given, then we can write an expression for the enclosed charge is just the linear charge density times the total length L as shown in equation D. Substituting the charged enclosed function to the electric field equation, we have the equation for the electric field generated from an infinitely long wire. For an infinitely wide thin sheet that is electrically charged, where the electric field is radiating outward of the sheet, the charge is defined by the surface charge density as shown by equation 12. The Gaussian surface is depicted as a cylindrical shape here. Sample problem. Use Gauss' law to find the electric field caused by a thin, flat, infinite sheet with a uniform positive surface charge density sigma. Using Gauss' law equation, we calculate the electric field generated, shown in equation 10. Solve for the electric field and take into consideration that the area here refers to the cylindrical Gaussian surface. There are two areas that we have to consider here. First is the side area, which is a curve which we call area 1, and its orientation is perpendicular to the electric field. So the electric flux is given as equation A. The second are the areas at the ends, which the flux equation is given as B. Note that both areas have the same angle with respect to the electric field, hence we simply multiply it by a factor of 2. So we use the function that has an electric flux and solve for the electric field. Here area 2 refers to the area circle, so we have equation C. Now we need to obtain an expression for the charge enclosed using the surface charge A density, so we have equation D. Substituting this back to our expression of electric field, we have the value of the electric field due to an infinite sheet. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening, and see you next module.